afternoon and welcome. I thought as it was the first session after lunch, it was a good idea if we turn the lights down. It'll make it easier to sleep, more comfortable, that sort of thing. What I want to talk about in this session is really what we're thinking about in terms of Oracle for the future of the Java platform. So Java SE 8 and beyond. Now, we released Java SE 7 in July this year. That was really a big change in the sense that we actually released something. Because, I have to be careful what I say here, don't I? Because what happened was, as custodian of Java, and I worked for Sun for 14 years before we were taken over by Oracle, obviously we'd been through the development of Java. We'd gone through everything from 1.0, 1.1, 1.2, 1.3, 1.4, 5. Clearly that was a triumph of marketing over engineering because we changed from 1.4 to 5.0. Then we had Java SE 6. And that came out at the end of 2006. So there was a long gap between the last major release of Java and Java SE 7. And a lot of things happened in the time between those releases, not least of which was the acquisition of Sun by Oracle. But there were a number of things that happened during the time at Sun which delayed the release of Java SE 7. There were things like JavaFX. There were things like open sourcing the JDK, which actually took a lot more engineering effort than we at first thought. So we had a number of things that needed to be resolved. We had a number of issues in terms of the technologies, the way the JCP worked and things like that in order to get Java SE 7 out. And so Oracle acquired Sun, plans were made, and so we now have Java SE 7. But we also have plans for Java SE 8, Java SE 9, and beyond. So when it came to Oracle acquiring Sun and therefore being the custodian of Java, we wanted to make it clear what the priorities were in terms of moving Java forward. What do we want to do with Java? Because a lot of people had concerns about Oracle acquiring Sun and, in effect, taking over Java. A lot of people were concerned that Oracle is an enterprise company. It's a database company. It does enterprise applications and things like that. So the concern was that it was just going to be Java for the enterprise. Java on the desktop, Java embedded, Java mobile was all going to be very much second-class citizen. There wasn't going to be any work put into that. It was just going to be enterprise Java. But what we've made really clear is that that's not the case. Oracle is very committed to Java in all different forms, and we really want to help Java move forward in all the different ways so we can increase the use of it. So we want to grow the developer base. Lots of different surveys have been done. Lots of different people count the number of Java developers, and depending on who you look at and who you believe, it's somewhere in the millions of Java developers. It certainly is a very, very popular programming language. Maybe it is number one, it kind of vies with C and Objective-C in terms of usage, but it very much is one of the most popular programming languages. We really wanted to increase the number of developers using it, because if we make Java successful, obviously the commercial implications follow on from that. So grow the developer base, grow adoption, increase competitiveness. Make it a language that people want to use because it addresses the needs that they have in terms of developing applications, in terms of the platforms they're using, and things like that. And adapting to change, because the types of application that people are developing are changing all the time. Web 2.0 applications, much more web interaction, mobile interaction, all of those sorts of things. So we really want to make it clear these are the priorities that we have, is to make Java as popular a language as we possibly can in all different ways. When it comes to changing Java, we need to be very careful about how we do that, because there are some very clear guiding principles that have been used throughout the lifetime of Java in terms of developing the language. When Java was first created and James Gosling and various other people got together and made the Java language what it is, they really were very concerned about making Java a readable programming language. I'm sure that everybody here knows that it is quite possible to make Java completely unreadable, because I've certainly worked on some projects where the Java code is very difficult to understand what people are doing. But in terms of the syntax, in terms of the way the language worked, really the guiding principle was to make it as easy to understand what was going on as possible. And so, there's this idea of code should be a joy to read. Okay, well, that's probably taking it a little bit too far, but the idea is to make it easy to understand, easy to see what's going on. So when you're doing things in terms of maintenance, you don't have to put in so much effort to understand what kinds of things the developer is actually dealing with. So quick show of hands, if I can actually see here. Who's ever used Perl as a programming language? Oh, actually, quite a few people. Good. I certainly worked on one project which used a lot of Perl, and I rapidly came to the conclusion that Perl is a write-only language. Essentially, once you've written it, it's almost impossible to understand what it is you've written. Now, I'm being unfair to Perl because it is a very powerful language, and it takes very few characters to actually do an enormous amount of things in Perl. But for those of you who've used Perl, I'm sure you realize that it can be a challenge when you come to maintaining other people's code or even your own code. We wanted to avoid that sort of thing with Java. Similarly, we want to try and avoid the problems of hiding from the developer what the compiler is doing. So if the compiler is suddenly changing things underneath in terms of what the functionality of your code is, that can again make it hard to understand, hard to actually modify code and maintain it. So this was the sort of thing that we were faced with. We wanted to continue to develop Java, make it a very useful programming language, address the needs of developers, things that developers wanted, but not really breaking it from the point of view of making it a readable language. And from the point of view of actually having the Java language evolve, we have this thing called the Java community process. The idea of developing standards in an open way, but not one which takes a long time to actually take place. Now, I am actually saying that with a straight face, because the Java community process has had some issues in the past. I don't want to go into that because a lot of them are very political in terms of various things that were dealt with in terms of the way that the JSRs were developed, various things around that. But what we want to do now is to make the Java community process, the individual JSRs, more transparent. So there's this whole idea behind JSR 348. So we're using a JSR to develop JSRs in terms of making the process more transparent. Having access to mailing lists and seeing what is going on in the expert groups as the specifications are being developed. Now, I know at the moment that there are some issues around that in terms of getting access to mailing lists and so on. And I've seen a lot of comments on the web and people sending in comments and things like that about the problems that they're having in terms of getting this thing. We are working on it. We are trying to address that. We're aware of these things. It's not from any malicious reason on the part of Oracle. A lot of it is down to getting the necessary legal things in place, making sure all of the structure is correct, and so on. So this will change. It will get better. Similarly, we've reformed some of the JCP in terms of the expert group. So there are various people who've been added to the executive committee. So we've got SueJava now, who's one of the, probably the biggest Java user group in the world, who are based in Sao Paulo. And they have literally tens of thousands of members, most of whom don't turn up to every meeting. And they're represented by Bruno Souza, who is a Brazilian, who is very vocal. He likes to let us know his views, and that's very good. We also have people like Goldman Sachs, who are representing more of the financial services community. Obviously, people like banks and the financial organizations are very big users of Java, so it's useful to have their point of view in terms of what they want moving forward. And then we've got the London Java community, who are already here. And so they now have a seat on the executive committee, and they are providing feedback and telling us what we should be doing with the JCP and so on. So there's lots of work going on in that respect. So just one slide on Java SE 7, because, as I say, this is already out there and you can download it and you can use it. What we did with Java SE 7 was really to break it into two pieces. So Java SE 7 is really Java SE 7 Part 1, and you could say Java SE 8 is the rest of Java SE 7 as was originally planned, plus some other things. And you've got various changes, small changes to the language itself. So you've got things like strings in switch statements. You've got the diamond operator to simplify generics. You've got the try with resources in order to simplify the way that you can close resources instead of using a try finally block and things like that. Class libraries, improvements around I/O. We now have some simple ways of doing the complex things like copying files and moving files. It's, it is quite amazing it's taken us that long to get to that point. The fork join framework, which allows you to simplify the process of dividing up a number of tasks across a number of processors, making it easier to have those things all happen in parallel and have the synchronization at the start and at the end handled automatically. We've also done a lot of work on the virtual machine, the inclusion of a new bytecode, invoke dynamic, which simplifies the ability to, or simplifies the process of having dynamically typed languages running on top of the JVM. We want to make the JVM appealing to languages other than Java. So things like JRuby, Jython, Scala, so on, things like that. It makes life easier in terms of the performance. So we get a much bigger performance improvement on those things. The other thing that's happening is the convergence of the JVMs. Oracle already had the JRocket JVM that they acquired when they got BEA. And by acquiring Sun, they got the Hotspot JVM. And the decision was made that you didn't really need two separate virtual machines, two engineering teams working on the code base and so on. So we want to converge the two machines into one. Not quite sure what it's going to be called. I think it's like Hot Rocket or JRocket, no, JHotspot or something like that. But the idea is to take the Hotspot code base and use that as our code base and then add features from JRocket to that to make a converged JVM. And a lot of work has already gone on in that respect. We've got the engineering teams integrated, and there's a lot of synergy in terms of the work being organized there. So let's move forward into the idea of Java SE 8. Now, I said that the idea of how we wanted to move Java forward, some of our goals were around about adapting to change. And one of the things that we need to adapt to is the way that hardware architectures are changing and will change in the future. So this slide came from a paper that was written by Herb Sutter, and he looked at the way that Moore's law had been applied to processors. So we've had this concept of the number of transistors that you can squeeze into the same size piece of silicon, doubling roughly every 18 months. And what we've also seen, certainly up until about 4 or 5 years ago, was that clock speed also went up at a similar kind of rate of change. But then about 4 or 5 years ago, we ran into this sort of problem, if you like, which was a number of physical laws. So heat dissipation, clock skew across a processor and things like that, which meant that increasing the clock speed became harder and harder. So rather than increasing the clock speed in order to improve performance and adding more transistors, what we've now been doing is looking at the idea of adding more cores to the same processor. So rather than having one core that executes one stream of instructions, we now have multiple cores that can execute streams of instructions in parallel, sharing the caches, sharing the various aspects of the processor. So if you look at the hardware that Sun developed and Oracle have now acquired, we had the idea of the SPARC T1 processor. And this had 4 cores in it, all of which could process 8 streams of instructions through pipelining and overlapping of the instructions and handling the approach to the arithmetic unit, cache, and so on. So that gave us the ability to process, in theory, in parallel, up to 32 threads at the same time. We then had the Spark T2 architecture, which came out in 2007. This increased the number of cores in the chip to 8, which gave us the ability to have 64 threads processing simultaneously. And then this year we came out with the Spark T3, which had 16 overlapping pipelined instructions and 8 cores, giving us 128 threads happening in parallel from the point of view of the operating system. So this is a challenge from the point of view of programming. How do we actually get things to work in a parallel way? Now, we introduced things like the ideas of the concurrency utilities in Java SE 5, and we introduced the fork join framework in Java SE 7. But it's not just about servers. It's not just about the idea of server-side computing, which is getting more cores. Now, the effect of Moore's law and that kind of thing is rippling down into mobile devices. So if you look at things like phones, there are now a number of dual-core phones on the market. Tablets, desktops are getting more cores. So NVIDIA have announced the Tegra architecture, which will have 4 cores for a tablet. You'll have a 4-core processor able to execute things in parallel. So what this leads us to is, how do we approach that from the Java perspective? Yes, we have the ability to create threads in Java. Yes, we have the concurrency utilities. We have fork join. But we need to do more. So Java SE 8 is looking at how to improve support for multiple processors. So, disclaimer I have to state here is that the syntax that I'm going to use in the following slides is possibly going to change. It's still something that we're working on in terms of developing the features for Java SE 8. So what I'm going to tell you about now is quite likely to be very close to the syntax that will be used, but there may be some changes. I know that over the last few weeks, there have actually been some changes in the syntax around some of the things I'm going to talk about. So beware that this might not be the final version of the syntax. So this slide, I'm fairly certain this syntax won't change in the next release because it's fairly simple code. This is a very typical sort of thing that we have in Java. So I've created a class which has certain properties associated with it. In this case, it's going to be a student. Now, a student has a name, a student has a graduation year, and a student has a score. So we've got those things encapsulated in our object. And then we want a collection of those to represent all the students that we have in our class or our university or wherever. Now, a typical operation on that might be to look for certain pieces of data. Searching for data is something we do an awful lot. So we could do that in a loop. So we say, okay, we've got our collection of students. We're going to iterate through that collection of students, and we're going to look for all the students who graduated this year. And then once we've found students who graduated this year, we want to determine who got the highest score. So we'll use the math method, max, and we'll record which is the maximum value. Very simple bit of code, but the problem is, how do we make that parallel? How do we actually take that and apply it so that if we've got tens of thousands or millions of records that we want to search through, rather than having to do it in a sequential way, how do we apply it in a parallel way and take advantage of the processing power that we have through multiple cores? Well, we could take the approach of using the fork join framework. We could split it up into subtasks. We could have those processed independently. Those could be applied to different threads on different processors, and everything works in parallel. Problem with that is that even though the fork join framework is very well designed, the approach requires a lot more code. So you have to write a lot more code in order to have the piece of work actually execute. So it would be nice if we could find a simpler way of approaching the problem. Now, the thing is with this is that there are certain aspects of this that we're really interested in, and most of it is not really too important. So we have a collection of students. We're interested in the students whose graduation year is 2011, and then we want the score from those students and look for the maximum value. Okay, so we could do that using a set of methods which take anonymous inner classes as the way of performing the functionality of that method. So what I want to do is I want to say, okay, here's my students. I want to filter this set of students based on some new class, or new interface, which I'm going to call a predicate. And in this case, it's going to be a predicate interface, or it's actually an abstract class, which takes one method. And so here I've got the operation, which is going to be looking for graduation year of 2010. Okay, that was a typo, it should be 2011. Then I want to map the data from that record in terms of the actual information that I'm interested in. So in this case, I'm going to map using an extractor object or class, and I'm going to say, okay, in this case, I want to implement the extract method, which will return me the score associated with that student. And then I'm going to reduce the results based on this new reducer interface, and I'm going to actually implement that and say, okay, give me the maximum value of those scores. So we're still doing the same thing that we had before, we're just organizing it in a slightly different way now so that we can have a number of different methods invoked in order to have that happen. So inner classes and anonymous inner classes are something that was introduced way back in 1.1 of Java. But they're not really ideal in this situation. They're very bulky in terms of their syntax, because you end up with, you have to implement the inner class, you then have to have the method of that inner class, you've then got to put the code in it, and so on. And for anybody who's used these a lot, you'll know that there are issues around things like non-final local variables. Unless the variable that you're accessing outside of the inner class is a final, you get a compiler error. There are also problems with what's the meaning in terms of return, break, continue, and this in the sense of the inner class. It gets confusing, it's a little hard to understand what's actually going on, and so on. So we have problems there. And similarly, non-local control, flow operators, all of these things mean that inner classes are an imperfect way of doing closures. Many programming languages have closures. Java doesn't have closures at the moment. Now, what we use is the single abstract method type. We use this a lot in Java. So if you look at things like runnable, callable, all of the event handling that happens in AWT and Swing, the comparator class, all of these use single abstract method types. And what you end up with is this typical type of piece of code, where you've got your method that you want to do something, and then you need to pass it a class which implements your interface. And in this case, it's going to be a callback handler, which has a single abstract method. You implement that callback method, and you're going to print out something. The noise-to-work ratio is 5:1, because all you're really interested in is the fact that it's system.out.println c.v. That's all you really want to happen. But you've got to surround it by 5 lines of code, or 4 lines of code, in order to have that happen. So what we're doing in Java SE8 is introducing some people, it's not really closures, it's lambda expressions. A way of simplifying this whole way of doing things. So what we end up with from the example we had earlier, where we want to take our set of students and we want to look for the highest score in that set of students, is a new syntax. So now we're going to say, okay, take the students collection and we're going to filter that, but rather than passing an anonymous inner class, we'll use a lambda expression. In this case, we're going to say that the student S is the parameter that we're passing, and what we want to process on that, the body, if you like, of the method, is going to be returning if the graduation year is 2011. And then similarly, we have a map method where we're passing in a lambda expression, where the parameter of that expression is the student again, and what we're returning is the score associated with that student. And then finally, we're going to have the reduce method, where we pass in the value 0 as our starting point, and a lambda expression which takes 2 arguments, a max and a score, and then returns the max value of the max and the score using the math.max method. So that all looks good because it simplifies things a lot. We've gone from almost a whole slide's worth of code, just a few lines of code. But we can do better than that because the compiler can actually do some type inference. Because if we look at what we're doing there, the compiler can figure out certain things. And we can actually end up with a situation where we can say, well, okay, we know that S is of type student because it has to be because it's coming from students. So we can simply say, okay, now we'll take the parameter S as being our student from the collection. We'll then return the graduation year being 2012 true or false. We map S again to the score. And then in our reduce method, what we'll actually do is use a method reference. And we can simply say, okay, just use math hash max to represent the maximum method. And that will, the compiler will then expand that out into the correct code. So we end up with a lot simpler piece of code than we had before. Of course, this doesn't actually solve our problem, does it? Because what we wanted to do originally was to say, well, how do we make this parallel? How do we make it so that we can divide this work into a number of processors, a number of threads that we have available to us? So the simple answer is to simply introduce a new method above that where we simply say, okay, take all our students, and then we'll do this in parallel. We'll filter, map, and reduce. So what parallel does, we don't need to care about. That can happen underneath, and we can deal with all the complexities of enough threads, pooling of the threads, and so on. We can deal with all the complexities of actually having the synchronization and the data and so on, all handled by the parallel method. And so we end up with a situation where we can now allow people to do things in a simple way in terms of trying to make their code parallel. So some more examples of our lambda expression idea. So we can specify our lambda expression as being a type, which is the parameter, and then the body, in effect, which is what's going to happen based on that parameter. So you can think of a lambda expression in some respects as like a pointer to a method. So we're treating a method almost as an object reference. So now we have a parameter context C, and the body of that is going to be to print out the value of C.v. We can use type inference, which we already sort of said in the previous slide, so we can simply say C as the parameter and print out C.v. The compiler will infer the type for us. And we can have simpler expressions where we can simply say, okay, int x is the parameter that's being passed, x plus 1 is the result that we're returning from that. Now, there are some rules associated with how we use lambda expressions. What the body actually has to be is, in effect, a single abstract method type. So we can only use a lambda expression where we would use a single abstract method type. So here, the callback handler makes sense because it's context and it's a print line statement, so that would be possible to replace that with a single abstract method type. Similarly, x plus 1, we could also do things like a runnable or an executor. All of that will work quite happily. But if we were to say something like object O equals, and then we've got an empty parameter, and we're simply going to return 42, that's actually not a legal thing, because it's not something that you could replace by a single abstract method type. So that would be rejected by the compiler. There are some other restrictions, because you need to think about this in terms of as if it was a method. So what you're going to have in the body of the method is a list of statements, just like a method, but no break or continue at the top level, and the return type is going to be inferred from the unification of the returns of the set of the return statements. So that's quite a complicated explanation. But it basically means if you've got a single way of returning, then the compiler will figure out what the return type is. Return from the body of that effective method, then the compiler will look at the types that are being returned and then figure out whatever is the lowest superclass of those types. Now, it could be object, because that's obviously the superclass of all objects. But if there's a common supertype, then it will infer that as being the return type. From the point of view of this, if you reference this within the body of your Lambda expression, then it will have the same context as if you were referring to the this in the immediate outer part of that Lambda expression. So you can use this and refer to the enclosing object. And you can use effectively final variables. What this means is that in the same way that anonymous inner classes can only reference external variables if they are final, what we do with the Lambda expressions is we say, you can reference a variable outside of the Lambda expression body if it has the final qualifier associated with it, that's okay. But if it doesn't have a final qualifier associated with it, and adding the final qualifier would not change the code from a functionality point of view, then you can still reference that variable. The net effect of that is that you don't have to explicitly mark all of the variables that you're going to use as being final, but they have to effectively act as if they were final variables. Because if you can change them, then that would make them, you couldn't use them in this context. So the other thing is, okay, so we've got our code where we're saying, okay, this is what we're going to do. So we're going to have filter, map, and reduce, and we're going to operate those things on our collection. Obviously, if you are a skilled Java programmer, you'll notice a slight problem with this. The slight problem is that if you look at the collections interface, or collection interface, you'll find that there is no filter, there is no map, and there is no reduce method. Okay, so we could take the collection interface and we could add those methods to that. There's a very big problem with that, which is backwards compatibility. Because if we suddenly add more methods to the interface collection, which is used very widely in Java at the moment, what's going to happen is that if you've got compiled code and you suddenly start trying to use it with new code, which uses these methods, you'll find there's a mismatch, because the classes that you've created using the old collections interface won't match the use of new methods, and you'll get a runtime exception because things don't match up. That will be very, very bad, because it will break potentially lots and lots of code. And we don't want to do that. So how do we get around the problem of adding methods to an interface without breaking compatibility? Okay, so what we're going to do is we're going to say, okay, let's have our interface, and we'll have an extension method. So now we're going to say, we'll add the reduce method to the collection interface, or in this case, the set interface, but we're going to add a reduce method to that as an extension. And then there will be a default method that will be made available from another class, in this case, the collections utility class, so that if the compiler finds that the collection or the set class that you're using doesn't have a reduce method associated with it, rather than it throwing a runtime exception because it can't resolve that method, what it will do is it will say, okay, I need the reduce method, I will use the reduce method that is provided in collections. If one is already there, obviously the method gets resolved to the method in your collection class. If it isn't there, it goes to the collections class and uses that one. So we end up with a situation where we can add methods to an existing interface and not break backwards compatibility. So now we have our new collection class where we have 3 extension methods. We have filter, map, and reduce, all of which have default implementations which are made available through the collections class. So this solves a lot of problems and makes life a whole lot easier in terms of how we can use Lambda expressions in Java, how we can do that in a backwards compatible way so we're not breaking existing code and so on. So the next big thing that is destined for inclusion in Java SE 8 is something that has been discussed for a long time. And this is Project Jigsaw. Project Jigsaw is all about how do we look at modularity for Java. We've had this concept of jar files, ever since the beginning of Java, so that you can put together a number of classes, put them in a single archive, and have them accessible so that if you want to reference classes from a library, you can reference them from within a jar file. But the problem is that jar files have some limitations. Considering how they were designed, we've managed to do very well in terms of extending them, really to their logical limit. But there are things that we need to do beyond that. We certainly need to address a number of limitations in jar files. We need to address a number of limitations in the way that they work to make Java more flexible. So here's an example of how we might start a Java application. You simply call Java as the application we're calling, and then you pass it in the class which contains the static void main entry point. So, okay, org.planet.jdk.aggregator.main, and off we go. Very unlikely you're actually going to see your command line like that. It's going to look a lot more like this. So you have your Java, you have your class path, which is going to include a number of jar files, because you can have lots of jar files with the different libraries that you need for your application. So you're going to have your $apphome, lib, jdom 1.0, Jackson 1.0, saxpath, Rome fetcher, jodatime, tag soup, and so on. And I'm sure if you've written any big Java applications, you'll know that these lists of jar files can get very, very long. Yes, in Java SE 5 or 6, I think we introduced this radical new idea of a wildcard, where it allowed you to say, okay, you can include all the jar files in a particular directory rather than having to specify them all on a single command line. That made life simpler, but it still didn't address a lot of the problems that we have. So we look at this. What we're really interested in is only certain parts of information there. So obviously, we want to execute Java. We want to run this within the JVM. And the jar files, we're interested in the name of the jar files. We don't really care too much about where they come from. We just want those jar files. And then we want to know where to start the application from. So we want to know what is the main entry point for this application. Obviously, we're specifying all of this on the command line, and it becomes very unwieldy to do that. So the idea behind Project Jigsaw and modularity in Java is to introduce a module.info.java file. And what this is going to do is to allow us to specify, in effect, a set of metadata for the application so that the JVM or the compiler can understand more about what are the requirements of this application in terms of external dependencies and also how we actually want to start the application. So we end up with a module.info.java file that will be associated with our application. Within that, we specify the name of the module we're creating. So it's going to be called org.planetjdk.aggregator. And then we will have a version number associated with it. And this is really one of the kind of big differences between modules and jar files, is that jar files never had a consistent way of handling version numbers. Yes, you could put a version number in the name of the jar file, but there was no standard specified way of handling that version number. With the module.info.java file, we'll actually have a standard way of handling that. So we'll say that the aggregator module we're creating is version 1.0. It then requires a set of different jar files which have version numbers associated with them. So we'll say, okay, JDOM is version 1.0, TagSoup is version 1.2, and so on. And the compiler can use this information to resolve the jar files that it's going to use to compile your code. And if there are different versions associated with that, it can pick out the right version that it needs in order to compile correctly. Similarly, when you run the application, the JVM will be able to figure out from your module path, not class path, module path, that these are the requirements, these are the version numbers that are required, and so it will pick out the right version of the module file in order to actually have your code execute. And by specifying the main entry point, we make it easier from the point of view of the JVM starting up so that you don't have to specify that on the command line. So what we end up with is a way of specifying all the dependencies between the different parts of our system. So we've got our module that we specified here. We've got a number of jar files or module files that we depend on. So we can specify, okay, these have dependencies. But then we can also say, well, okay, JDOM actually has other dependencies which we don't see directly. So now JDOM, or Roam Fetcher as well, okay, so we can see that there's a dependency path there, and we can figure all of that out. And both the compiler and the runtime system can figure all these things out and make it work using the right versions of the different module files. So what this ends up with is ultimately the death of ClassPath, which I'm sure some people will be fairly happy about, because it's been one of those things that Java has, right from the very beginning, it's always been a bit of a problem in terms of using the ClassPath correctly. Now, the other thing is that what we'd like to be able to do is use this information in other ways. Because, okay, if we've got the information about our dependencies, if we've got the information about the main entry point, why don't we have ways of actually creating a jar file from that, a module file from that, but then also we could create installable packages directly. So we could create an RPM file, we could create a Debian file, and have those automatically generated using all the dependencies, collecting all the different modules together, and putting it into a single installable package. And then in theory, we could take that one step further, and we could say, okay, well, let's go from our Maven side and actually say, right, we know the dependencies, we know our build tree, just take everything we've got and generate from that our executable, our installable package, and make life simpler for you as developers. So yes, ClassPath should hopefully go away, but this has other advantages, which is that we can now not just apply the modularization to your applications, but why not apply the modularization to the JDK and the JRE itself? One of the very powerful things about Java is the fact that we have so many class libraries available to us. So there are literally thousands of class libraries and methods that we can access within Java. But I'm willing to bet that nobody uses all of those methods and classes in a single application. Very unlikely. So for example, who here uses Corba in Java? I'm not seeing any hands at the moment. Okay, so that's a good example, you see, because Corba is still in the JRE, but most people don't use it. So why do you have to install the Corba classes from the class libraries in order to have your application run? Wouldn't it be nice if we could break up the JRE into a number of sections so that when you want to have your application install and run, you don't have to download all of the components of the JRE at the same time in order to get your application to run. You can download the JVM, you can download the core classes, you can download, say, AWT, you can download Swing, you can download networking, all of the different pieces you need in order to get your application running. And that way you have the minimum subset of components available in order to get your application started. Then as you have the ability and time, networking connection, and so on, you can gradually download the rest of it so that other applications which require different components can then take advantage of those. So we're not breaking the idea of write once, run anywhere. We're not breaking the idea of having, lots of different JREs which have different subsets of components in it. Still be one JRE with everything in it, but broken up in such a way that when you want to install and get an application running, you can do it much more quickly than you can at the moment. So that improves not just the footprint, but also the performance of startup for applications. So that kind of leads us to the idea of profiles and modules, because if you look at good old Java ME, we had this idea of the profiles so that you could specify different subsets of APIs that would apply to different types of devices. So we're looking at the same approach for Java SE. So you can have a Java SE base profile, Java SE base module, and then have additional modules and profiles that can be specified on top of that in order to add things for, say, a user interface. So you've got maybe Swing, maybe JavaFX, like I say, networking, whatever pieces of web services, all those sorts of things. that you might want to use for different types of applications. So this is really the proposed contents for Java SE 8 as it stands at the moment. Again, this is liable to change. There may well be some discussion around this. This is not the definitive final list. So we've got Project Jigsaw, we just talked about. We've got Project Lambda for the idea of the Lambda expressions, the convergence of the JVM, where we're bringing in features from JRocket into Hotspot. There will be a version 3 of JavaFX. There's the possibility of bringing JavaFX into the Java runtime environment. That's something that's still up for discussion. Improvements around JavaScript and integration with JavaScript. So there is a new JavaScript engine that we're working on. This is a thing called Project Nashorn, which will give us tighter integration around JavaScript and so on. Device support. This is sort of more related to user interfaces in JavaFX, making use of things like the accelerometer in mobile devices or even in laptops, cameras, GPS, all of those types of things. Some things around the language itself, so the idea of including annotations on types, so it would extend the use of annotations as we have them at the moment. And then, of course, further changes to the class libraries and the APIs, some improvements around security. Finally getting the JSR 3.10 and the date and time sorted out. Date and time is one of those things that is just like a bit of a nightmare to get it all absolutely correct. So there's various things that we're looking at in terms of improving APIs. So some additional disclaimers. So some of the ideas I'm going to talk about for the next few minutes are really very speculative. This is beyond Java SE 8. So this is Java SE 9, Java SE 10, and beyond. All of these things are very much, like I say, ideas rather than solid things that we will be putting into Java. A lot of them will require a lot of research and development in order to make them work, in order to fit them in a way that will enable them to be seamless in integration, possibly. Maybe some of them will even break backwards compatibility. That's one of the things that is actively being discussed, is whether we want to say, okay, let's draw a line where we will actually make changes to Java, which will mean that old code will need to be changed. Sun have always been, and Oracle, have always been very, very committed to the idea of minimizing the changes that you have to make to working code to make it work in order to move it to a new platform, a new version of Java. But we may get to a point where we decide to make radical changes that will break backwards compatibility. Some of these things might turn out to be bad ideas, some ideas might be added, but the future is still bright. So from a Java SE 9 and beyond point of view, there's a number of areas that we're looking at. So interoperability, the idea of the multi-language JVM. This builds on the work that we've done with Invoke Dynamic and the DaVinci Machine project. Cloud computing seems to be a very popular thing at the moment. Lots of people are looking at software as a service, all of those types of ideas. So we need to address the requirements of cloud computing from the Java platform perspective. Ease of use. Things like self-tuning JVMs. Rather than having to use all these hundreds of command line options to fiddle with the different ways that the garbage collector works and so on. Wouldn't it be nice if you can just say, okay, let the virtual machine tune itself internally to make itself work the best way for that application. Some other optimizations around data structures, type system, and so on. I'll talk a little bit about that in the next couple of slides. And the idea of really examining how we can make Java a single platform and moving away from the concept of Java ME as being a separate thing from Java SE. Java ME was a great idea when devices really were very radically different from a processing power point of view. With Moore's Law and the last 15 years, clearly now Java SE can be applied to many more devices than it could 15 years ago. So interoperability, this is the non-Java languages running on top of the JVM. Obviously, we've got Invoke Dynamic, that's been done. Java and JavaScript interoperability, that's something we're working on. There's Project Nashorn, Java JDK 8. Meta Object Protocol, this is an interesting idea around actually having the JVM change the way that it does things internally, driven by your application. So your application can actually interact with the JVM to redefine things like how you do method resolution and resolving methods, things like that. Lots of optimizations around the JVM that we're looking at, again, to improve performance of non-Java languages on top of the JVM. That'll be JDK 9+. Java native, JNI. JNI is one of those things that doesn't get an enormous amount of use, but when you do, it's quite a hassle to actually write all the code that you need in order to make JNI work. And I don't know whether it's true or not, but somebody did tell me that JNI was deliberately designed to be complicated to use to discourage people from using it, which doesn't sound like a great design decision to me. But what we want to do is simplify JNI. So the idea is JDK 9, there are some ideas around making JNI much simpler to do. Cloud, like I say, this idea of software as a service, platform as a service and things like that, requires things like multi-tenancy. How can you have multiple JVMs all running on the same machine and being isolated from one another, allowing different people to use different JVMs without interfering with each other, various things around thread groups. We had this concept a while ago, the MVM, the multiple virtual machine, where you could use a single instance of the JVM but effectively have multiple VMs running on top of it for multiple applications, and you could share various underlying aspects. We're looking at that again. Hypervisor aware, so cooperative memory page sharing, lifecycle migration, and so on. That's all beyond Java SE 9 at the moment. Language features, some interesting ideas here. So things like large arrays. Currently, arrays are limited to a 32-bit value, so you've got a limit on, well, you're always going to have a limit, but you've got a limit on how big you can make your array. We might move that up to 64-bit, so you can make really big arrays if you need to. A unified type system. This is one of those ideas of changing Java quite radically and doing away with primitives. Primitives were included in Java originally to improve performance. We don't really need that now because of the underlying performance of the hardware. So could we move to a truly object-oriented language and do away with primitives? So everything is treated as an object reference. That would clearly avoid a lot of problems that we have at the moment in terms of conversion and so on. And that sort of leads into the idea of reification. Could we change generics and make them like true generics? So avoiding the problems of type erasure so that you don't get that problem of things like that. True function types, going down the real closures route and actually taking things further in that respect. Data structure optimizations, looking at ideas around multi-dimensional arrays and structs and things like that, and looking at how other languages do things. So can we import ideas from other languages to make Java better, to improve its performance, and so on. A few things around integration. So there's modern device support. Already talked a little bit about this in JDK 8. So there's the idea of multi-touch screens, the idea of location-based services. Things like the sensors will probably be JDK 9 or so. And then, how do we take advantage of the latest advances in hardware? Things like the GPUs, offloading engines, doing things in terms of compiled SQL and stuff like that. So again, various things that we might want to look at to improve the use that Java can make of these types of things. So the important thing around how we do this is to have open development. So the concept is that the Open JDK project is now the development vehicle for Java. It's the development vehicle for new features that are going into Java, and it is the source code base for the binary distributions that Oracle create. So we create binary distributions for Windows, for Linux, for Solaris, and we're kind of working on the idea of Mac port. Apple decided to discontinue support directly for Java on their platform, but they very kindly joined the OpenJDK project and contributed the code so that we could take the features that we were creating and generate a binary distribution for the Mac. A lot of people were very happy about that. Looking at the number of little Apple signs I can see here, I'm sure that lots of people will be very happy about that too. So that is coming. It's only an engineering thing that's holding us back from doing that. There is an early access version of that available. So what we do is we take the OpenJDK source, we build our binary distributions, and we make them available through our website. What we're aiming for is a 2-year release cycle for Java SE. Originally, we'd sort of looked at 18 months as our release cycle for this, but it was decided that whilst developers want a very short release cycle so that they can get all the latest features very quickly, once you look at the people who are deploying it, they don't want a shorter release cycle because testing and certification, all those sorts of things, becomes a really big headache if every 6 months somebody's coming out with a new version of the platform. So our roadmap, right up to Java 12, as we're currently stating it, is JDK 7 was launched this year. Next year, you'll see some more work around the JVM convergence, and you'll see the Mac OS X binary distribution. JDK 8 is scheduled for around about the middle of 2013, and taking a 2-year release cycle beyond that leads us to the logical conclusion that JDK 9 will be sometime in 2015, JDK 10 will be 2017, JDK 11 will be 2019, and JDK 12 will be all the way out in 2021. So I'm trying to work out at what version of JDK I will retire. So yeah, but we've got a roadmap going a long way into the future. So really the conclusion about this is that the Java platform will continue to evolve. It is something that Oracle are absolutely committed to in terms of making sure that developers get what they need from the language. It's not going to be the next COBOL. We don't want it to just sit there and people carry on using it and then they move off to other languages and it gradually decreases in usage. We want to make Java a vibrant and changing way of programming. So Java SE 8 adds some nice big features. Java SE 9 and beyond could be some very, very interesting features. Lots of discussion, no doubt, will have to go on around that. Just to a couple of places for more information. The OpenJDK project is where everything is happening. So if you're interested in looking at more of the details around Lambda, then openjdk.java.net/project/lambda, and Jigsaw, same place, project/Jigsaw. And then I have to put the following slide up, which is this is one of the things you learn when you move from Sun to Oracle, is that every presentation you do has to have a legal statement which says that everything I've just told you is not to be used as a basis for a purchasing decision. But thankfully, since we don't buy Java, it should be fairly easy. So with that, thank you very much.